Hello, everyone. This is Jeff Wilkerson, professor of physics at Luther College. This is an introduction to an experiment to sort of check to see how good a job relativity does in explaining the energy momentum relationship, kinetic energy momentum relationship for some electrons that leave a trail in a bubble chamber. And so we're going to be doing this in general physics this week, and so this is our introduction to this experiment. We may use it for other experiments at other times in other courses or in other places. So what you have is this photograph of a track of an electron that's spiraling down in a bubble chamber. So a bubble chamber, you've got a hydrogen bubble chamber. Donald Glaser won the Nobel Prize for building the hydrogen bubble chamber to measure energy momentum of particles like this. I went to graduate school where Donald Glaser worked. And so, the story they told there, I don't know if it's true, the story that they told there was about how he was feeling like things weren't working. He wasn't going to figure out this problem that he wanted to do. And so he kind of had his head down looking at bubbles rising in his beer and realized, oh, maybe we can create bubbles and measure this track of bubbles in a hydrogen chamber like this. And so in any event, this is what we've got. You put this electron, the electron's charged, you put the electron in a magnetic field, and we know very well, we've done this experiment already, that particle is going to circulate. As the particle loses energy, that curvature, radius of curvature, gets smaller and smaller and smaller. So you get the particle spiraling in like this. And so that's what we got this photograph of. You can see it spinning off other particles in other places. It's an interesting image to look at. And so what you want to do, your job is to say, you can figure out the kinetic energy. You've been given a relationship that says, here's the kinetic energy, here's the path length as a function of kinetic energy. So you think about these electrons flying through this material, and they're giving energy to the material, they're slowing down, slowing down, slowing down, slowing down. And as they slow down there and give up their energy, then they spiral in like this. How far they go? This is the range. Think of this as the range, is how far these electrons can travel in liquid hydrogen at a given kinetic energy. And so as they slow down, they're going to give up their energy more quickly. So as they're going really fast, zipping through there, we call these men ionizing particles. As they go through really fast, zipping through this material, then they're giving up the same amount of energy in each section of path length through the material. But as they slow down and start and sort of crawl to a stop, they're giving up more energy in this path length. And so you have a region down here where this is not linear. It rolls in, and then you have a pretty good linear region. And we want to make sure we're working in the pretty good linear region right here, which by and large, what that means for you is don't get too close down here to the end. Don't make this S too small. S is the path length. So suppose you pick a spot right there. S is the path length that it takes from there to the end to get down to the end of the spiral path. So this is what we're going to do. We're going to look at this, and we're going to say that's how much path length you have left. That's S. And that's going to tell you the kinetic energy at that point where it started. Right here, you got a longer path length. You got more kinetic energy. Here, you've got a smaller path length to get into the middle. You've got less kinetic energy. So what we want you to do, let everybody in the lab do this. Everybody can have a picture here in front of them, and everybody can have a map roller. We're going to use a map reader to actually try to track along this path to measure that distance. Okay, and then so we know that distance, that's S, that tells us the kinetic energy. We're going to measure the radius of curvature by trying to figure out, to say, okay, let's draw a tangent line at this point and draw a tangent line nearby, and where those tangent lines all cross, we draw perpendiculars to those tangent lines. Where they all cross, that's going to be our radius of curvature. We're going to see that's the center of curvature for that point. So that's the work we're going to do. All of this is laid out for you in the experiment guide that's out there. And so that's the work we're going to do. So we're going to try to measure radius of curvature, which is going to give us with the expression that we know how the radius of curvature is related in a magnetic field. We know the strength of the magnetic field here. And so that radius of curvature, and we know the charge on the electron is related to the momentum of the electron. So that's going to give us the momentum. This is going to give us the kinetic energy. And we're going to compare the momentum kinetic energy relationship for this particles, this electron, and see how we can, which one's better. Does relativity do a better job of describing this, or does Newtonian mechanics do a better job of describing the trajectory of these particles? And are they the same, as we might expect if they're slow enough? In any event, so we walk through about how we're going to do that. You'll get down. So what everybody in the lab can have a map reader. Everybody in the lab can have this paperwork in front of them to do this kind of work. And so each person can measure 3 or 4 or 5 of these points, so that in groups of 2 or 3, you can end up with at least, at least 10, 12, 8 to 15 points, let's say. So you can end up with a bunch of points that give you kinetic energy. So then you can plot kinetic energy versus some function of the momentum down here. And I've offered a couple of suggestions to you of what those could be. One, that should yield a straight line if you've got a Newtonian mechanics description that works well for these particles, and a different one that would yield a straight line if the relativistic expression was better. And you can walk through it. I want you to explain to me why these different graphs are going to yield a straight line, what the slope would be and what the intercept would be. Okay? So then you fit your straight line. So you got your data, and you fit your straight line to that data. And then I want you to measure the deviation. So what I talk about in the guide that I've given you is to measure RMS deviations, the sum of the RMS deviations. So think about it this way. If you've got a graph like this, and there's a data point, there's a data point, there's a data point, there's a data point, measure how far that is, and measure how far that is. So the line predicts, at this given x value, the line predicts what the y value should be. Your data point isn't right on that line. So if you take your data point minus what the line predicted and square it, and then square root it. So basically, we're just turning it positive, okay? So you've got this root. You take the square of the deviations. What RMS means? It means root mean square. So you take the square of the deviation, square of the deviation, square of the deviation, square of the deviation, and find out what those mean deviations are. So let's do it that way. Let's find out what the mean deviation is, and then take the square root of that mean deviation for each of these two fits, and then make an argument for me about which of these fits is better. How you think that this root mean square deviation technique is going to help you decide between these two graphs, which one you think is better. For the one you think is better, then we're going to do what we've been doing lately, which is we're going to see what the linear fit suggests the best slope is, what it suggests the intercept is, and we're going to compare that to the theoretical value. So that's what we got for you this week. Is one other thing I want to make sure you want to do on this chart right here. There's a scale up here so your reader, your map measurer is measuring some distance. But this scale is not. This isn't the actual track of the particles. There's a bigger track in the bubble chamber. I think it was big. Anyway, this isn't the actual path, and this sets the scale for you. So if you take your map roller and roll it along this scale, it'll say, this many centimeters in the picture is equal to this much rotation, this much measurement on my map measurer. So then you can use that as a conversion to say, okay, I've measured this much on my map measurer right here. This conversion tells me what that actually is in centimeters in physical space. And so I can use that to go over here and measure the kinetic energy down that way. So that's what we're trying to do. Should be a fun lab. We'll see you there, everybody. Take care.